Okay, so this is a lecture about how to estimate elasticities. On your homework, you're going to be estimating elasticities in two ways, and I'm going to show you how to do that here. So I already tried this once. That's why you see all the writing on the screen already. It got screwed up, so I'm doing it again. Okay. So what are we talking about? The cool thing about econometrics is that we get to estimate things that we learned about in microeconomics or macroeconomics. For example, elasticities. So what I'm showing you here is we have, on this graph, we have two examples of a demand curve, one that's inelastic, the steeper one, and one that's elastic. And so in micro, you learned about elastic demand curves and inelastic or elastic supply curves, etc. Now we're going to actually use data to estimate these elasticities. Suppose we, our example is going to be the demand curve for gasoline. So our demand curve here is Q gas. We're going to put the quantity on the left-hand side. We're going to make that a function of the price of gas because the definition of elasticity is here. The definition of elasticity is a percent change in P affecting percent change in Q, or what if we change prices by 1%, what percent is the quantity decline? So we know that quantities should decline from economic theory. That's why the demand curves are always sloping downwards. So this elasticity formula indicates that when prices go up, quantities should go down. So what percent do they go down? That's the question that we're trying to answer with an elasticity. So we're estimating a gasoline demand curve. So the population function is here. And the sample is here. Sample regression is here. So we have Q hat gas equals 30 minus 3.125 P gas. So the coefficient estimate beta 1 hat is 3.125. Now we have an elasticity formula down here. Here's our estimated elasticity. So the elasticity is really just dq dp times p over q. So dq dp, this portion here, dq dp that I'm circling in blue, what is that? Well, that is by definition, beta hat 1. So dq dp is beta hat 1, negative 3.125. So in our elasticity formula, we can just plug in negative 3.125 for dq dp. So that's what we're going to do. We're going to plug in negative 3.125 here. And then for p times q, or p over q, this portion here, we're going to take the averages of the prices and averages of the quantities, or the average of the y and the x variable, and plug those in. So in your homework, you're going to take the average of the variables and I gave you code to do this in the R script. Just plug in the averages of each of the variables, the y and the x variables. And so the average, suppose we get the average quantity of gas is 50. Here, I'm circling that in green. The average price of gas is 3.2. We'll just plug those values in here. And then the elasticity estimate, do it in rainbow, is negative 0.2, which means that a 1% change in price causes a 0.2% decline in the quantity demanded of gasoline. So that's one way to estimate an elasticity. This is method 1. Method 1. Now the other method requires changing your variables a bit. And so I'm going to do a little bit of a tutorial on what do I mean by changing your variables. So the regression that we're most used to, or that we're used to at this point, is the level regression. The level regression, where we're regressing the level of y on the level of x. This is the regression we've seen so far, one single variable regression. The interpretation of beta 1 in this regression is a 1 unit change in x is associated with a beta 1 change in y. We could also log the dependent variable. So that's the next line here. The log of the dependent variable. It's a natural log. I wrote regular log above, but the natural log of y regressed on the level of x. The level of x. And so how does that change the interpretation of the regression when we log a variable? And well, first of all, how do we log a variable? I've given you code to do this in the R script as well. We are creating a new column in our data set that is just the log of the y variable. So we log every value of the y, and that becomes the log of the y variable. The interpretation of beta 1 in this case is a 1 unit change in x is associated with 100 times beta 1% change in y. So we're still dealing with a 1 unit change in x because x has not changed. But now, because y has changed, we're talking about percent changes in y. So the log changes it to be interpreted as percent change in whatever variable we're dealing with. So in this case, we're logging y. So this is a percent change in y. How about if we logged the x variable? So now let's go to level log. Level log. If we log the x variable, but we leave the y variable in levels, so we have y regressed on the log of x with our intercept and our slope parameters, beta 0 and beta 1. The interpretation of this is going to be a 1% change in x. So now we have a log of x, so that's a percent change in x. The log of x, a 1% change in x is associated with a beta 1 divided by 100 unit change in y. So in the previous, the log level regression, x is levels, so that's a 1 unit change in x. In the level log, x is in log, so now we're dealing with a 1% change in x. So in the log level, we have x is in levels, so we have a 1 unit change in x. In the level log, we have x in logs, we're dealing with a 1% change in x. And then vice versa, in the log level, y is logged, and we're dealing with a 100 times beta 1% change in y. In the level log, y is in levels, so we're dealing with a beta 1 divided by 100 unit change in y, not percent change in y. So that leads us to the log regression. So we've logged the dependent variable, we've logged the independent variable. What if we log both? What if we log the dependent variable and the independent variable? So in that case, we're going to log y and log x. So we're going to regress the log of y on the log of x. The interpretation is a 1% change in x is associated with a beta 1% change in y. So that is the definition of an elasticity. So beta 1 in a log-log regression is a direct estimate of an elasticity. That's pretty nice. We don't have to do any post-estimation conversions. We don't have to multiply the beta 1 coefficient by p over q like we did up here in our first example of how to calculate an elasticity. Here we had to multiply the beta 1 coefficient by p over q. Now we don't have to. Now in our log-log regression, the estimate of beta hat 1 is an elasticity estimate. So let's suppose we estimated a model where we're regressing the log of Q gas, the log of the quantity of gasoline consumed on the log of the price of gas. So we're estimating a log-log model. That's this is our population regression. Our sample regression down here is the log of Q gas hat equals 2.4 minus 2.23 times the log of the price of gas. The nice thing here again is that the beta hat 1 estimate is a direct estimate of an elasticity. So the elasticity in this case, percent change in Q over percent change in P, is just negative 0.23. So a 1% change in price causes a 0.23% change in the quantity of gas consumed. So that's great. We have two ways. This is method 2. Method 2. Two ways to estimate elasticity. One, up here, is we're going to estimate a level model. We're going to take the coefficient, the beta 1 hat coefficient estimate, and multiply it by P over Q, or the average price and the average quantity in this case. We get negative 0.2. If we estimate a log model, we directly estimate the elasticity, and we get negative 0.23 beta 1 hat coefficient estimate. Don't be surprised if you get slightly different estimates in your homework. Using the two methods, that's going to be normal when you're estimating something in two different ways. Good luck.